Hello everyone. So last time we have ended with four kind of quantum systems which are displayed here if you can see so. So let's get continue with that. So the four models actually we are dealing with are particle in a box, rigid rotor, uh, quantum harmonic oscillator and hydrogen atom. As you can see, these are the energy formulas for these four models, and particle in a box is regarded as an electronic spectroscopy. These are the electronic energy levels, and rigid rotor is for the rotational spectroscopy, and harmonic oscillator is for vibration spectroscopy, and H atom is for the atomic spectroscopy. So we can move forward. So So I will tell you what actually absorption and emission means. Let's say you have a material and you find the emission spectrum or absorption spectrum for this. Let's say it is emitting a, um, a 8 photons. You counted that there are 8 photons it is ejecting, and meaning each photon is actually released by one atomic transition. And let's say you have another metal which is giving same wavelength, same frequency photon, uh, now 6 photons. Like photons are particles as well, so there will be finite particles will become emitting, right? So this one, emitting 8 photons, and this one emitting uh, 6 photons. And so here emission intensity is high. Intensity means number of photons ejecting out. Here it is low intensity. So this is coming, so intensity is actually the number of photons ejecting. Let's say you have another material and you have 8 photons ejecting same, but the frequency is different. This is high energy photon and there are 8 photons coming, meaning 8 transitions are parallelly happening, and 8 transitions are equally spaced. I will tell what is a single transition from a molecule emits only one photon. If 100 photons are emitting, meaning 100 transitions are happening at once, meaning there are 100 molecules available. We can quantify like that. So if you draw wavelength versus intensity plot, so let's say you got here. So it's a bigger wavelength compared to this. So this how the emission spectrum looks like. Then if you take for second one, here it will be little small peak because the intensity is here it is 8, 6, and here it is 8. So the height actually represents how many photons are coming. And the same here, if you see, it will be blue shifted. It will come near because the wavelength is smaller, and 8 photons. You can now you might have understand how to interpret the emission and absorption spectrums. So 8 photons emitting, meaning there are 8 molecules of the population, and 6 photons mean there is 6, and 8 here also again 8. So if you draw energy level diagram, so these two electrons are like exciting to up and coming down. So here parallelly there are 8 photons coming, meaning there are 8 homos and 8 LUMO states available. So 8 HOMO available, and 8 pairs of electrons available. So here the ground state population is total 8 pairs of electrons. So they have finite spacing of their subsequent energy level. So this is HOMO LUMO. So they will emit a monochromatic radiation. This is called monochromatic radiation, meaning single wavelength of all photons emitting out. There is no distribution of different wavelengths. Single monochromatic wavelength is emitting 8 times, meaning there are 8 molecules are releasing, each molecule releasing one photon. And here, yeah, and here if you see, the gap is higher compared to this. This is smaller energy compared to this. So here if it excite and relax, then you will get a high energy wavelength, which is actually result of a smaller wavelength. So here also 8 photons. 8 homos available and 8 electron pairs of electron available. Here also same, but here the population is only 6, so that's why you will get less. So whenever some people draw like absorption spectrum, they will only draw one HOMO and one LUMO and say they will say, and they will draw only one electron pair, and they will tell that this electron will exit and relax, that is the wavelength it is coming here, they will say. But you have to understand that here, if four photons are coming, meaning here there are four similar energy states, degenerate energy states, we can say degenerate energy states here, meaning same energy level. There are eight, we couldn't visualize here, but actually you can write here as 8 lines and 8 like 4 pairs of electrons will be here. That is the meaning of this diagram. So people simply draw like this, but you have to understand in your back mind that back end that there are if 4 electrons, 4 photons are coming, meaning here 4 homos are available and 4 homos are available, and if we excite these and when they relax they will emit this radiation. So now you might have understand this diagram and emission mechanism. So let's categorize the spectroscopy based on photons wavelength. If you got like a very small wavelength, meaning the energy is very high, if it is UV region, then it is actually electronic transitions, and this is the this is the gap looks like. And for IR, which is actually vibration spectroscopy, the energy is little bit smaller compared to the UVs. Here wavelength is bigger and frequency is smaller compared to UVs, so the gap will be smaller. And yeah, so in a one pair of energy levels in electronic transitions, you can find three or many also. So like the comparison, I am comparing the energy level gaps between the electronic and vibration, and if you see rotational it will be even smaller, very small. This is called quantization. Here quantization is very high. uh, you can see it's very high, like the next energy level is available here only, but here it is little bit like narrowed, and here even it is narrowed, here it is very broadened. So you can see that as we go down, energy of the electron is smaller, then actually you have to understand that the quantization is smaller. So this is actually the birth of actually quantum mechanics. So that quantization, like the energy is actually quantized and wavelength is quantized. First they found that wavelength is quantized, then they interpreted that different molecules are different, releasing different kind of wavelengths, meaning each mediated by different kind of spectroscopy, and a molecule can have all three combinations of transitions, like this you can include here, this you can include here, and that superposition spectroscopy is called rotational vibronic spectroscopy. You can merge these two, called vibronic spectroscopy. Electronic plus vibration is vibronic, and if you want you can merge these to also raw vibrational spectroscopy, and if you merge these three all, rotational raw vibronic spectroscopy. So I will, that is a little depth topic, I will explain it again. So these are the energy gaps between these spectroscopies. So you can find that the energy spacing between electronic is higher than vibration and higher than the rotational. This will be in visible region and this will be in IR wavelength, and this is in microwave wavelength. You can see here the different regions of the electromagnetic radiation. So if you start, visible will be here, IR will be here, microwave here, radio will be here, and UV, X-ray, gamma are here, very right side. So this is how the electromagnetic spectrum looks like. So if you have temperature, if you heat a sample, they will radiate UV. They will radiate photons. How? Because if you heat, the electrons will take that heat energy and they will excite and they will relax. That a relaxation and emission energy is actually this. So if the body temperature is, if you increase, they will release this frequency. So you have sun is very high, um, very highly uh, having temperature, right? So it will release this much high frequency emission. Likewise, you can see the very low energy one are radio waves. The wavelength is around 1 kilometer, and microwave will have in micrometer, and infrared will have zero point 0.1 micron, and visible will have in nanometer. In ultraviolet also it is in nanometer, and in X-rays it's angstrom, and gamma ray will be in picometer, which is equivalent to atomic nucleus. You can see this is the spectrum. This you have to understand, and here are I given the wavelength ranges. You can see radio wave will be having more than 1 millimeter, microwave wave will have 1 millimeter to 25 micron, and infrared will have 25 micron to 2.5 micron. And people only talk in nanometers, they won't like to call in micrometer. So actually they will use another convention called wave number. They will talk in centimeter inverse wave numbers for IR and microwave radio waves. They will talk in terms of wave numbers instead of in length scale. They will take a wave number scale. So selection rule. I will tell what is selection rule. So in last, this is very important topic. Selection rule. Many people will like confuse what is happening here. So actually, let's say you have this set of energy levels, and you have, let's say, 4 electron pairs, and you will fill in energy levels one by one. So one pair will fill here, another pair will fill here, another pair will fill here, another pair will fill here. Fill here. If you excite now, the topmost electron will only get excited. These will be stayed like this only. So out of them, which is the highest filled molecular orbital is E4. This is highly filled molecular orbital, which is called HOMO. And there are infinite energy levels. There are infinity. Among them, which is the lowest unoccupied molecular orbital, which is E5. So the electrons will actually excite from highly filled orbital to lowest unoccupied molecular orbital. So this electron pair we can only excite to E5. We cannot directly excite E6. It will only take in discrete manner. We can only excite in discrete manner. We cannot excite E4 to direct E6. That is called overtone. That is called overtone, but it is not allowed in some spectroscopy. In electronic spectroscopy, it will be only allowed in uh, discrete in stepwise of one. Only step of one they will excite, and in which step of one only they will relax. So the other steps are not allowed. This rule is called selection rule. So if you like incident photon, single photon, which is equal to this gap, this electron pair will excite. Otherwise it won't excite. This will transparently come out. This photon won't interact and it will come out. If it is less than this gap, it won't react. If it is greater also, it won't react. It have to match this gap. Then only this electron pair will absorb and it will excite with a step of one only. And now we again, if you shine like incident photon, it will again excite in a stepwise manner. And this is what plus one, like a step of plus one only, quantum number change happens. This is what selection rule means. And if it comes down and release in a stepwise manner, that is also minus one, like change in quantum number will be in step of one. That is the selection rule. So here selection rule or transition rule is plus or minus one. So yeah, among all three spectroscopics, each spectroscopy has its own transition rule. Electronic spectroscopy will have plus or minus one, and rotation will have also plus or minus one, but vibration can have any. You can excite in vibration spectroscopy from here to directly here, anywhere in the energy levels you can excite. but the first one excitation is fundamental excitation. Then if you excite to second one, it is called first overtone, and for second, if you excite directly, then it will be second overtone, like that. Yeah. So if you selection rule 2 means change in quantum number 2, meaning you can only excite in a step of 2 only. It is not allowed in a step of 1. And minus 2 means also same, like you can only relax also in a step of 1. Yeah, with a step of 1 only. This one it will come back here, so it's like that. So again it will come with a step of 2. This is what emission spectrum will finally comes. Yeah, I hope you understand selection rules and transitions and different comparison of the energy levels of different spectroscopy. Thank you.